In this talk, I'm going to talk about like lambda returns and then argue why they are good and then why they are bad, and also introduce like a new version that I'm working on. So, what is a value function? The value function of a state following a policy phi is the expected sum of discounted rewards. Mathematically, we can write it as this. Now, the trick is we can express the value function of one state in terms of the value function of other. So we can write v phi of s as the expectation over the immediate reward that we get, and the expectation of the rest of the rewards that you see in the trajectory. What this means is we get like a one-step Bellman operator where we express like the value function of current state in terms of the value function of the next state. And then we can sample the returns from this operator, and then we can run towards that operator. But interesting thing is that like we could generate like a range of operators by unrolling the rewards differently, and then by summarizing the rest of the rewards as a value function differently. For example, one could generate like a n-step operator by unrolling the n rewards and then summarizing the rest of the rewards as a value function at that point in time, and then we get an n-step operator. Now, now that we don't know, we don't have like a prior knowledge about like which n is better than other n, so we don't know how to choose or set the value of n. Now, what do? We take the convex combination for all the n-step operators, and then we design a new operator. So we call it like lambda operator, where we take like a convex combination of all the n-step operators. So the lambda operator is given by this expression. So 1 minus lambda and then lambda, the coefficients that weigh the different n-step returns. Now we have the lambda operator, but is this actually calculating the expected discounted sum of rewards that we want? We can show that like the lambda operator that we have is actually in fact calculating the same expectation as v phi of s. To do this, we start off with the value function, the definition of the value function, and then we express each reward in the expectation as a convex combination using the lambdas. Now that we use lambdas for all the rewards, we will get like these expressions. Once we get these terms, we can collect terms with like similar coefficient. For example, like we had like each rewards weighed by 1 minus lambda, 1 minus lambda times lambda, 1 minus lambda, lambda square, and so on, right? We can collect like all the rewards which has the same coefficient before them, and then once we do that, so we can write each of the rewards as like summation of different terms. Now, what we can do is like we can take the expectation on that summation, because taking the expectation with respect to policy phi inside this expectation doesn't change the value. So we take the expectation inside on these summations again, and then we express each of the expectations as like one-step return, two-step return, and so on for all the n-step returns. This is what I mean by that. So we take the expectation of each summation and then express as like different n-step returns. Now we have like a whole suite of like n-step returns that we can have, and then each of them are weighed by lambda, and then we can concisely write this as like a lambda operator. We start off with the same expectation that we want to calculate, which is the expected discounted sum of rewards, and then we end up with a different operator from which we can sample and we can do stochastic approximation algorithm. But essentially, we'll be estimating the same value functions that we care about. So this particular operator, we call it like lambda version. To summarize, these are the different operators. There's one-step operator which takes into account the immediate reward along the trajectory that you see, and then it summarizes rest of the rewards as a value function, and it bootstraps from there. We have this n-step return which collects like n different rewards, and then after it collects n different rewards, summarizes the rest of the things with the value function. And then we have this lambda operator which takes into account each reward that it sees along the trajectory and also each value function that it sees, and then takes some combination of that. Now, you may ask like why is this important, or like what are the benefits that we would get from this kind of a operator? First thing that I can say is that we get faster conversions. Because like we are taking into account like each and every value functions that we see along the trajectory, but also the rewards that we see. So we get more information about the trajectory, and hence like by appropriately selecting the lambda, we get like a faster convergence. This is the image taken from Sutton's textbook. So here he plots like various curves for different lambdas against the root mean square error that he got in the first 10 episodes. As we see, like for a particular value of lambda, we get like a faster convergence, and we require like a lot less samples. The second thing is like choosing a lambda would avoid you hyperparameter tuning alpha, because like some lambdas are like robust to learning rates, and then that's what we can see here. There are like two plots here. Like one is the offline version, which is the forward view, and the other one is the online version. So either of the versions are good. TD. Yeah, so when lambda is 0, so you fall back to TD, and when lambda is 1, like you. Alpha is the learning rate.
Okay.
The benefits, so some of the literatures reported state-of-the-art performance using like lambda returns. So this is also a good benefit if you, yeah.
For the pre-results, are there these plots that it basically is the faster convergence a theoretical property, or is it just?
So these plots are generated on like an empirical experiment. So it's like a sequence of states that you have, and then you run like 10 trajectories or 10 episodes on those.
Is there also theoretical results?
Yes.
Yes. I mean,
yeah. But only for linear function approximation.
Not additive.
So we get like state-of-the-art performance. And then the second thing is like temporal credit assignment. So if we were to look at the backward view or the online version of lambda returns, what it does is like at each point in time it receives some error, and then it tries to assign this error into some states in the past that it has taken along the trajectory. So by controlling the lambda, we can control how much credit we want to send to the state seen in the past. When your lambda is high, we are assigning like a lot of credit to the states that we have seen in the past, and when the lambda is low, we assign the credit to the immediately seen state. This lambda also helps us solve temporal credit assignment problem. And the next thing is like bias variance trade-off. So if we set like lambda to be too low, then we are like very biased in the sense that we always bootstrap on the value that is very immediate to us. But if we set lambda to be really high, then we collect like a lot of rewards along the trajectory, and we also take a lot of value functions, and hence the variance of your estimate increases. So the value of lambda also plays a role in the bias variance. And there are like certain versions which also emphasize certain states, which we are going to talk about in detail more. So we can have like a state-dependent lambda, which emphasizes the confidence on a certain state, and we can bootstrap more from those states. Confidence in the value function of the state. So let's say you have like you have estimated the value function of a state directly for a particular state, then you want to bootstrap more from that, because that has like a better information about what's going to happen in the future.
What would be the factors that make some states value?
Maybe the kind of rewards, deterministic or stochastic, that you will see from the future, number of the state transition probabilities, and how many branches that you can branch from that state.
It's definitely like I'm missing some intuition here. It seems to me like almost all of these properties you could also get from just changing n in n step rewards. And you started off by saying there's many possible n's and we don't know which n. I don't understand why taking a combination of all of them, like maybe n equals 3 is just the best one. Why would we want to take a combination of all?
We don't know.
So, but it's just this is lambda is also hyperparameter too. So it's just somehow a more robust
This has like a historical problem here. So when so back in like a decade ago, people don't have like big memories for doing reinforcement. It is eligibility traces, those linear things, they come first, which is like a backward view of the PD lambda comes first. And they are like very practical to use for those kind of computers. And then later they found that you can actually view the updates using the eligibility traces using a forward view, which is this is like coming from a very practical method. It's from the different direction.
I see. So these older methods, which actually got benefits from using eligibility trace approaches, are no longer applicable in deep learning, or no longer like what makes
just said it reaches state of the art on the thing.
That's true. Okay, so
that's the forward view. Like you compute the lambda returns, and then you choose that as your target, and you try to estimate that you increase a gradient towards that target.
So the equivalent of the two views can be established if you are using, can be theoretically established if you're using linear case using some kind of correction. But here I assume they just assume they are equivalent and they compute.
So then can you share some intuition for the eligibility traces, why those are important or helpful?
Why those are important?
Because like end step. That's the thing that I'm stuck on.
Versus end step. So lambda returns versus end step is that question I can answer. So let's say you fix like some value of n, right? First thing, you don't know any information about what n is better than the other n. So you have to hyperparameter it. And then second thing, even if you fix a particular value of n, you would only be bootstrapping from one value function in the future. The temporal difference is with respect to only one value function. Because you collect like rewards for n steps and then you consider one value function. Whereas as opposed to if you choose like a particular value of lambda, you're collecting rewards as well, and you're also bootstrapping from value function. It gives you like more information to what might happen in the future.
But we can talk about that. Yeah, I guess I just don't really see where the more information is coming from. You have all the same rewards.
So let's say this is n step, right?
Yeah.
You only have like information about what's going to happen in this triangle. But if you were to choose like lambda returns for a particular value of lambda, you have information about outer triangle and then this triangle and then every triangle at each point in time. So you have like a wider scope.
But the one-step triangle contains all of that, right?
Yeah.
Right. I mean, I get that part, but I just don't see. It just seems like you're turning a different hyperparameter. I don't see.
So bootstrapping function is off, right? And you have other ones that contain that future too, but you can correct better than that function. That's what you have.
You have some stochastic reward. Every reward you observe means that every target that you update your value function towards has a variance and values there, and MSE there. If you use other target constructed by the lambda return, that will give you lower MSE.
Okay.
Also related to the variance and the variance, like you have you initialize your say your value function randomly. Like to do bootstrapping that kind of number.
So okay, I think we can talk about it. Yeah, I'm convinced you're right.
And then people also use lambda for off policy corrections. And then we have like quite a few literatures on how to choose optimal value of lambda, like what's the better value for lambda. For example, it started off with like setting the value of lambda to 1 over ns, where ns is the number of times that you visit a particular state. Set your lambda value to that. The more you visit to a particular state, the more confident you are about the value function, the better you can bootstrap and better you learn the value of that state. And then they also said another direction is lambda is set equal to the state transition probability. So if you're transitioning frequently to a particular state, then your lambda for that state should be high for the same reason as before. And some analysis yielded like a different version of temporal difference, which is called like phase PD. And then they developed a schedule for lambda. And then there's a greedy approach which considers like a one-step bias and variance, and then they set the lambda to reduce the one-step bias and variance. There's like meta gradient style, and there's also like patient gradient style. So there's like quite a lot of literature on this. But each of these versions are limited in a certain way. So if you are choosing a particular value of lambda, you see your application and then pick the value of lambda that you think is right for your application. Now we talk about the details about like what's bad in that. So far we have a question.
For example, one of interaction. Yes, people have to look at it.
Summarize like the optimal lambda is like not a solved problem, and we still don't know like what's the right way to set the lambda. So let's look at the state-dependent lambda. So the idea of state-dependent lambda is to emphasize certain states, in the sense that if you want to bootstrap from a certain state, and if you are confident about the value of that state, you set your lambda low so that you're bootstrapping more from that state. And if you are not confident about a certain state, you set your lambda to be high on that state. Yeah.
The terminology question is lambda returns a general term for any convex combination of n-step returns, or is it? I was thinking specifically about this like.
Only lambda can take values outside the interval of 0 to 1. If you can take outside the values of 0 and 1, it can be generalized to express any kind of. But if not, no.
But so
the way I see it is that like any method that accounts for all the rewards that you see along the trajectory and all the value functions that you see along the trajectory, you can call it like a lambda.
So it's not about the exponential decay.
It's not necessarily be like you can have like a different way of like discounting each return, and then that would still be like a version of lambda returns.
I see, and so that's what you're about to talk about.
Not that actually, but yeah.
Okay.
I think that's fine if you agree that that's the.
So coming back to this, like the state-dependent lambda, we set the lambda to be low on certain states that we are confident about. So recall that this is the lambda operator that we have, and then we can write a sample of this operator as this guy. Like we take like one sample and then like write it recursively. And then to get the state-dependent lambda version, we replace the constant lambda with the state-dependent lambda. So the equation above becomes the equation at the bottom, where we say like we collect the immediate reward, and then we have the lambda parameter for the state, which is at one time step in the future, and we take like 1 minus lambda times the value function of that state into a target, and then we keep repeating this recursively by multiplying a gamma lambda factor. So that's your state-dependent lambda. This particular version of state-dependent lambda has like two particular problems. Like one is like dampening effect, and the other one is cutoff effect. So the way they go, the way they make a jump from the usual lambda returns to state-dependent lambda returns, that's the reason for having like these two problems that I'm going to talk about. So this is the lambda state-dependent lambda operator. So let's try to analyze the updates on a example. They are also like the certain lambdas that depend on the state, but then they are applied to off policy setting. I'm talking in general, like not specific to off policy or on policy. Still in terms of like the returns, just value function and returns. let's take a toy example. We have like a sequence of states that go from S0 to S5, and at each transition you get like a reward. Let's say S3 and S5 are the states that have like a good value function, in the sense that we are like very confident about the value function on that state. And for the rest of the states, like let's say we don't know much about, we don't have much information, or the value function is not very accurate. This is a setup, and then for the dampening, to show the dampening effect, we consider the lambdas that are highlighted on the red. So we set like the lambdas of S3 and S5 to 0 because we are very confident on those states. Set rest of the lambdas to 0.5. This is just a motivating example. Now, if we analyze the returns, if we analyze the target for the updating of state S0, this is what we observe. So we have like reward 1 that we collect, and then we have like the 1 minus lambda, which is like 0.5 times the gamma of value of S1. And then we have like 0.5 gamma of S2. And then as you see here, like the dampening effect has already started happening because we are multiplying the lambdas of the past states into the 1 minus lambda in the future. So this lambda that multiplied gt plus 1, you have like lambda multiplied with another lambda gt plus 2, and then so on recursively. What we get is like you want to bootstrap as much as you want from S3, but then in reality, like you have this dampening effect due to the lambdas set between the state that you want to bootstrap on and the state that you want to bootstrap from. This dampening effect is highlighted here. Like
So even though S3 is highly confident, after S3 and S0, you have these low confidence states, and that's it.
Right. That is the target for S0. And then the second effect is the cutoff effect. For this case, like to avoid the dampening effect, what we can do is that we can say states S1, S2, and S4. We don't trust the value estimates as much as we want to. So instead of setting it to at some low value like 0.5, let's set it to 1, in which like we completely cut off the information about those states. But then this results in a different problem, which is the cutoff effect, in the sense that since we are multiplying lambdas like over the period of time at each point in time, so we multiply when we update when we get the value function of S3, we multiply 1 time the value function of S3. But when we go into the future, so this 0 gets multiplied to all the information in the future, and then you totally don't bootstrap from state S5. Here in this setting, state S5 is also like really confident state, and then we set the value of lambda value of that state to be 0. But then in reality, when we want to bootstrap, then the 0 that gets multiplied to that particular state kind of like defeats the purpose because you're not able to bootstrap from state S5. This is the cutoff effect. So to fix this, what we do is like we take a new approach, which is like additive approach to develop lambda returns. What we do is like we start with the value function definition, which is expected discounted rewards. Now, what we do is like at each point for each time step from time step t, I add and subtract 1 minus lambda times multiplied by the returns from that point onwards. What this means is we have the returns from here inside the expectations. I add and subtract like all the returns from time step t plus 1 onwards. I add and subtract like all the returns from time step 2 onwards, and so on. This is still like good because like overall we are computing the same expectations. Now what we do is like, since we can take the expectation of the quantities inside the expectation, like which is again like E pi, expectation with respect to pi. So we'll take expectation for some parts of the terms inside. In a way, we are not changing the value function. We are still computing the same value function, except that we are taking the expectation of some quantities here. For example, here in this case, we are taking the expectation with respect to all the returns from time step 1 onwards, and then all the returns from time step 2 onwards, and so on. Yeah.
So, lambda fixed for every.
Right now, I'm talking about like the general case of lambda. We'll go back to the state dependent lambda in a second. Now, yeah, as I said, like taking expectation on to one of the terms inside the expectation doesn't change the value of that state. What we do next is like we try to group all the terms which doesn't have any expectations together, and then we group we substitute the expectations with value functions, because this is nothing but the value function at that state, and this is nothing but value function at state, which is like 2 times steps away. So these are the terms that doesn't have any expectations. We can simplify these terms, and then we can write as like a nice concise summation, which is this guy. And then, like as I said, we can also substitute the expectations with the value functions, and then plugging these two information back into the thing gives us a new operator. Is this what it does? Is which one? So you're saying this is not right?
I don't know.
Weird, as in yes, it's because like we are doing additive approach. You are kind of like taking the it's like the way I see it is like you have the reward information at one point in time for the value function, right? If you consider the value, if you bootstrap from the value function completely, then you already got the expected in expectation. You already have the expected discounted rewards. But I'm saying like let's have some emphasis on that value function and then like push the over counting to the rewards. That's why you get like I minus 3 times lambda minus 1.
Each time you start summing from one step ahead, so that term would appear in t minus I terms before disappearing in the future ones. I have a question related to that. So you're adding and subtracting an infinite number of terms, right?
Infinite number of terms, yeah.
And there is no assumption to make about.
So next,
like each term is convergent, I agree with that, but adding an infinite number of convergent terms is not necessarily convergent.
I think the way I see it is like we're still approximating this operator, right? This is still like
right.
goes
But
from the t to infinity.
saying mathematically, right? Yeah, you're still adding zeros, but then you're combining them in different ways. So how do you still guarantee that those combinations are feasible? I'm not sure about my comment, but I feel like maybe some assumptions are needed there. Yeah, we can chat about the details, but I was just curious if you thought about that before, because we can still do the math, right? But
Yeah.
can we still do it? That's the question.
Yeah, so this is the operator that we will get. Now we can analyze the updates on, for example, with this new operator. So writing out like one sample of this operator, which I call it like a return. This is what I get. Now this is a dry example, and I'll consider the dampening effect now. The same setup as before, in the sense that we have the lambdas of states to be these guys. Instead, like we are using this operator now rather than the lambda operator. Now what we have is like we can see like at each point in time we are bootstrapping from the value function at the same proportion to what we try to emphasize. We want to bootstrap 1 minus 0.5 times the value function at state S1 and S2. That's what we are doing here, and then S3, which has the information like which we are very confident about the value function. So we are bootstrapping like the complete. Now the dampening effect is only due to the gammas. Dampening effect due to lambdas are avoided.
So this like new update or operator looks very similar to the GAE operator. They both stem from the lambda returns, right?
I don't know much about GAE. I think it's the convex combination of the TD errors.
Yeah, but over here also, the way you have an exponential gamma with the 1 minus lambda term, it's also there in the same way.
But we are not doing exponential averaging. Exponential averaging on it. That is still like multiplicative in terms of lambda, but here there is no multiplication happening, right? Coming up certain.
I think there's something weird here. Like you have a total coefficient of 2 on a value. 0.5 plus 0.5 plus 1. This is gonna, if you just assume the value of every state is the same, it's gonna be basically 2 times the value.
Yeah, so what happens is that like we have this reward coefficient, right, which is I minus t times the reward. Going back to the operator, we have this term, right? For the word counting that you're doing from the value functions, you're gonna give up certain part of the actual samples that actual rewards that you see. For example, if you're doing double counting 2 times, then for all the rewards that you see in the future, you subtract like two times the actual reward that you see from.
But I mean, just from the term you wrote there, it just seems like it's already too large, and all the terms assume everything's positive.
Yeah, but going forward, like the coefficients on the rewards would go negative, right?
Oh, really?
Yeah.
Okay, I understand.
In the sense that you're giving up some actual rewards that you see around. Yeah, so as I said, like the dampening effect due to lambda is avoided now, and the coefficients of the value function is exactly what we want, and the overestimation that what we are doing, like we kind of like give it away from the actual rewards that we see to a negative coefficient on them. And the second problem that we saw was like cutoff effect. So now we are in the blue setting where we set like the lambdas to be 1 on state S1 and S2 because like we don't trust them, and then like S3 and then S2 are the states that we completely trust, and then we want to bootstrap as much as we want from them. And writing out the update for this operator would kind of give that case to us in the sense that we're able to bootstrap the complete value function discounted by gamma, of course, for S3 and S5. And then the overestimation, what we are doing, we kind of like pushing it to the rewards, and then we are subtracting or we are having like an 80% of what. So yeah, so we kind of like bootstrap from all the confidence. So what do I want to do from this? Yeah.
I have a question. Here you use lambda to denote the.
Lambda is state dependent.
Yeah, and you put that lambda into your into your target, and you generate a sequence of weights, and you say that these weights are better than the ones.
What weights?
The weights for the value function and
these weights you mean?
You're talking about like the weights that generated by your operator is better than the weights generated by.
No. Yeah. In a way, that's in the sense that for the lambda here you have the cutoff effect in the sense that since you had like 1 here, you multiply this guy with 0.
Yes, but here you're assuming that the conflict, like for when you're comparing your operator to the lambda operator, you're assuming that the confidence goes to the lambda in the lambda operator.
No,
exactly.
Confidence is like 1 minus lambda here again.
Yeah, I mean, is that
It's
directly
the same thing.
connected? But if you generalize like lambdas to take the values of all the things you find, lambda return can also give you.
The lambda returns would never give you this because of the multiplicative effect, right? Because you have.
I mean, if the lambdas do not only take value in 0 and 1.
Sure, like let's say you have like a value of 0.1, right, on some state, which means that it's still like high value state. But if it's like 10 time steps away, then all the coefficients between state S1 and then S9, they kind of add up to the amount of bootstrap that you want to do from state S10, right? There's like dampening because of the coefficients that you set for the states in between. But in this case, like you don't consider the coefficients in between these two states to bootstrap from the state of S10.
In that lambda operator setting, you just treat those confidence as lambda. Directly, you just place the lambdas using those confidence.
But you can't do that, right? That's not what lambda.
But here in your function, the confidence is not only determined by lambda, but complex thing. Oh, you only substitute, you only replace the lambda within your complex thing, and you get another weight. This kind of comparison doesn't.
I don't know why you are saying that, but we can take it offline because like when you see lambda returns, there is like dampening effect due to the multiplicative coefficients of lambda, and that's what I'm trying to avoid by developing like an additive version. So we can take it offline and then discuss. Yeah.
Maybe a related question, but so if you forget about the need to multiply all the lambdas together, you just consider an arbitrary convex combination of an infinite number of n-step returns. Is there an equivalence, like for any particular states-dependent lambda plugged into this formula? Is there an equivalent convex combination of returns that could be read and returns that could be read?
Yeah, I would say no, because like as soon as you set some state lambda of some state to 0, anything that you're going to see in the future.
No, that's assuming there's multiplicative. Forget about the need to make it multiplicative. Assume we have some way of normalizing to ensure that all the coefficients do truly sum to 1, even in the infinite, right? So I mean, like this exponential decay is one way to do it, but assume we have some other way, and we can actually do it arbitrarily. So we can just say, all right, the coefficient for the first one's 0, second one's 0, third one's 0.2, fourth one's 0.1, etc. And somehow when we assign all of these, it does add up to 1. So if we're allowing ourselves to be that general, even obviously that's not like a mathematical do, but we assume we could do that. For any particular set of state-dependent lambdas method, is there some convex combination and separate terms that could be written out? If there's a correspondence?
I would still say no, because like in the sense that when you are weighing like instead of convex combination, like if you're weighing like equal or like any other proportion, you're weighing on the returns as such, right? So, but what here I'm doing is like I'm weighing separately on the values and then weighing separately on the rewards. So I set some coefficient for the value function and then I set a different coefficient for the rewards. I'm not considering the returns at all. It's just like the value function separately and then the reward separately.
So you think it's possible that there's something?
First guess is that, but then like I have to think more like if there is like some configuration of that. So where do I want to take this from is that like one thing is that I started off this because like assume like you have like some state like very much distant into the future and then you want to bootstrap from that guy. Right now the lambda of states like gives you the dampening effect and then you are not able to bootstrap. To avoid that, I want to do this because you can pass the information which is at like 3 time steps away faster into your current states. And then like the directions that I'm looking right now are like performance of additive versus the multiplicative version. The multiplicative versions are the lambda returns and the additive versions is like this version. And then we also get like more control over the way that you want to bootstrap from the value functions that you want to bootstrap. And then I want to answer the question if we can have like a better bias variance trade-offs here. And then the next one is like richer class of eligibility traces, which I haven't talked much about, in the sense that we have this exponential decaying version of eligibility traces in lambda returns. Now I want to see like if this version would give like a different combination or different like version of eligibility. And since we don't have like a clear-cut answer of what's a good lambda for a particular state or what's good lambda in general, so does this direction help me find like a or lead me to an easier route of finding like what is the lambda is. And then the last 2 points are something that I've been thinking lately about the time-dependent lambda and the role of lambda in temporal hierarchy. Time-dependent lambda, I think there are like you can vary your lambda along the episode, or you can set the lambda of states which kind of change. When I say time-dependent, you have like literally time-dependent in the sense that for every state, you set like lambda to a certain value which are at 3 time steps and to a different value which are at t plus n time steps and so on. And then you can decay them over the episode, so you can keep them constants. That's the secondary choice, but I'm also thinking on these lines. And then the role of lambda in temporal hierarchy, in the sense that lambdas give the effect of hierarchy in the sense that you are able to bootstrap from somewhere in the future into a current state. So this should naturally be like the hierarchy is what I'm suspecting. So these are just the future directions that I'm looking at. So that's it from my end. If you have any questions or any comments or anything.